thermal comfort, energy efficiency in building, and sustainable urban planning. And Indian Green Building Council Accredited Professionals, Dr. Gupta's research contributions are widely recognized with more than 20 international journal publications, several Scopus and Web of Science indexed articles, and multiple book chapters, including his authored book on housing, climate, and comfort. His expertise is further reflected in his involvement as a reviewer for reputed journal and his leadership in key institutional consultancy and government-funded research projects. Today, we are honored to have Dr. Gupta share his insights and expertise with us, enriching our understanding of sustainable design and energy efficiency in built environment. Please join me in warmly welcome Dr. Janmejoy Gupta.
Thank you, Architect Shubham, and thank you, NIT Patna, for inviting, and thank you for all the participants who have made time to attend this very FDP being conducted by NIT Patna. So, shall I begin?
Yes, sir. Yes, sir. Yes, sir.
Okay, I'll just begin. So, I hope my screen is visible to everyone.
Yes, sir.
So today we are going to talk on enhancing energy efficiency in hospitals through appropriate HVAC and other building services. Obviously, hospitals are a huge consumer of energy, and it makes much sense to enhance energy efficiency in hospitals through appropriate services, and especially the HVAC services. So if we look at healthy building services in hospitals, indoor air quality, infection control, energy efficiency, and patient comfort are the key words, obviously. And if we look at healthy building services, is basically about ventilation and indoor air quality, definitely. Appropriate pressure zoning in the regarding HVAC, appropriate temperature and comfort control, energy efficiency and sustainability, and as well as some other services which are also need efficient management, like water management, lighting, daylighting, acoustic noise control, smart building, and automation. So these all things with specific emphasis on HVAC and the indoor air quality as well as energy efficiency, which actually go hand in hand, will form the crux of this presentation. Now, there will be obviously overviews of the National Building Codes 2016, which provides guidelines, basic guidelines for healthcare facility design, ventilation, HVAC. There is ASHRAE 170, there is ASHRAE 62.1, there is ASHRAE 62.2, and there is ASHRAE 90.1. All these ASHRAEs will also be referred to American Society of Heating, Refrigeration, and Air Conditioning Engineers in Engineering Manual, of which and now the Indian version is ASHRAE, of course. So we'll be looking at all these basically in this presentation. So if we look at energy efficiency and healthy hospitals, the main factors, the main aspects are energy efficiency, appropriate material selection, HVAC, there are issues related to HVAC, and then in the hospitals, it's not only about energy efficiency. Energy efficiency and indoor environmental quality or indoor air quality and indoor air quality go hand in hand. So for that, we need to keep the indoor environmental quality also very fine-tuned. Energy efficiency, which leads to net zero in hospitals, is closely linked to improved indoor environmental and indoor air quality, obviously. Now, net zero concept is essentially, especially for India, too much a far-fetched thing. Very difficult to actually achieve fully net zero, because net zero by definition has to produce enough renewable energy to meet its own annual energy consumption requirements, thereby reducing the use of non-renewable energy in the building sector. Now that is a bit of a too tall a task. So we should rather be more pragmatic and say we want to maximize energy efficiency. And it's not that at present energy efficiency strategies are not being followed in hospitals. Many hospitals, especially the bigger ones, and some notable examples like the CMC Hospital, Vellore, Christian Medical College, main hospital in Ranipet in Vellore, just one example. They actually follow very effective HVAC energy efficiency strategies and overall services HVAC energy efficiency strategies. Some common methods which many of you here will be aware of also there for energy efficient HVAC, like energy recovery ventilation, ERVs, which reclaims cooled air, mostly cooled air, and in case it's heating is also required, heated air from the exhaust, reducing HVAC load. And actually, many are not aware of the fact that NBC 2016, our good old NBC and ASHRAE 90.1 mandate that ERVs are required in hospitals more than 10,000 meters square in area. Now, how many follow or not follow is a different question. And ERVs have been, if properly implemented, have been found to reduce cooling and heating load by 30 to 50%. Of course, other than that, there are the good old passive shading devices, solar passive design, which we are all very much aware of, optimized window wall ratio maintenance, following ECBC standards, etc., etc. Another one very common way of reducing energy when other option centralized systems don't really work is VRF, variable refrigerant flow system. That also helps. Now, since net zero is so much spoken about, but as I said, very, very difficult to achieve, we should be basically knowing what are the basic attributes of net zero. So metrics is very important, measurable. There should be measurable indexes and there should be measurement guidelines. Without that, net zero will be a very in the air concept. How much energy is exactly consumed, how much of it is being generated through renewable sources on site in the building, what are the energy use typology, what are the classification of the energy uses, etc. And as well, it should look at the comprehensive indoor air quality, because at the cost of energy, we should not hamper the indoor environmental quality, obviously, especially in a sensitive place like a hospital. So building consideration and values should never be sacrificed in pursuit of zero energy or so-called zero energy or enhanced energy efficiency, as is more pragmatically put. Now, ECBC has this standard thing, obviously, right, of prescriptive methods and whole building simulation methods, right? So the first one is whole building simulation method, in which they say that it's a performance-based approach and the total building, every aspect of it is looked into, energy modeling is done at the design stage, and the compliance is much more rigorous. And then there is a easier to do prescriptive approach where we measure it in terms of energy performance index mostly. The total annual energy consumption of a building should not exceed the total base case energy consumption computed as per ECBC standards for India. So it's all the provisions, basic provisions are there. It's not that nothing is there. It's there. For ECBC has it, for healthcare facilities is there, for every type, for commercial facilities is there, right? So the thing is where it needs to be implemented more, obviously. So if you look at the EPI approach, of course, EPI, the ECBC has a lot of standard guidelines like window wall ratio, which should not be more than 40%. And then in case the window wall ratio crosses the threshold of 40%, ideal optimized 40%, if it crosses that, then we should have special window glazing. Then solar heat gain coefficient of glasses is obviously very important. Then overall wall assembly U values have to be maintained at a certain, should not go above a certain point. Overall roof assembly U values should not go above a certain point. So all those are there in ECBC, clearly spelled out. Like in EPI approach they say that for the hospitals, the EPI range is usually a bit more. You'll find EPI range for normal apartments or normal office buildings is a bit lesser. So for hospitals, they allow till 275. for warm and humid climate. For composite, because obviously hospital energy consumption is much more than in an apartment or than in an office even, right? So they have this. So and they give points if based on the percentage of energy savings up and over the EPI. If you have 6% savings, you have 1 point. If you have 28% savings, you have 12 points. So all those basic strategies are there. It's in the implementation part that we are lacking actually. So before we go into the more serious parts of the presentation, obviously we are all aware of this, that basic spaces of the hospitals are there, and energy efficient planning should keep in mind the basic design considerations. And services become such an important thing in hospitals because obviously, as we are aware of, services including corridors and storage and mechanical rooms, etc., can occupy around 35 to 40% of the total floor area, which is more than any other building typology. Because hospitals are the most energy intensive services they require, and they require specialized services. The heart and soul of hospitals is services, and so they occupy a lot of total floor area. So it's all the more imperative for hospitals to have more efficient, energy efficient services in place. Now, zoning is a very important aspect in hospitals. Like, we can't have, airflow happening between the sterile and the non-sterile areas. So for that, what's usually done is positive pressure is maintained in some areas and negative pressure is maintained in other areas. Obviously, like water flows from a higher level to a lower level, like wind movements happen from a higher pressure area to a lower pressure area to equalize the pressure by the laws of basic physics. Similarly here, someone is unmuted. Please mute, otherwise I am having echo. Hello. So positive pressure is usually maintained in operating rooms, sterile storage, so that the air flows out. Negative pressure is maintained in isolation rooms, TV wards, which are infectious, contagious, so that the air flows in. The air from those contagious, infectious areas should not flow out. Obviously, common sense. And then there are neutral pressure. And all these have to be done by HVAC, obviously, right? Because it's mostly HVAC nowadays, or hospitals have to be. So all these special considerations, and for these spatial interventions coming, if the architect gets the basic zoning wrong, then these may all be very difficult to achieve, or even if they are achieved, they will include much higher expenditure cost, right? So the important thing is to actually do the basics correct, and then the rest follows. So if you have segregation of sterile and non-sterile, then clean and dirty traffic streams are segregated, obviously. Subzoning helps a lot. Staff, patient entry and exit are segregated. They need to be segregated. These are the basic design considerations, which may seem very simple, basic design considerations, which we even teach our students, or we ourselves learned in, say, semester 7 or 8 when we first time did hospital design. But these are where people still get wrong. I mean, it's not followed properly, either due to external factors or whatever. So these basic things, if done well, help in the more advanced things being done correctly. The circulation pattern needs to be streamlined. The OT, of course, needs to be kept sterile. So the OT may be sited slightly isolated away from general hospital thoroughfare. As I said in the previous slide, operation theaters are usually positive pressure, prevents contamination. ICUs, again positive, reduces cross infections. Isolation rooms like TV wards, infectious disease wards, because they contain an infection, they have to be negative pressure so that air cannot flow outside from those rooms. And sterile storage again will be positive to prevent positive pressure to prevent contamination. Now, indoor air quality is also a very, very interlinked concept along with this energy efficiency in hospitals, because they are very closely linked. And if one is compromised, the other is also often compromised. So a very important thing in hospitals is the air changes per hour, and which is actually defined as the volumetric flow rate of supply air divided by the volume of the ventilated space. and the ventilation flow rate. And all these proper values have to be maintained as per, usually in India, we do it as per CPWD guidelines. ASHRAE also has detailed guidelines regarding it, ASHRAE and ISHRAE. So whenever the duct system of hospital HVAC is designed, these have to be very properly maintained. And of course, purity of air, often carbon dioxide is used as a basic indicator. Now, if you look at air changes, which is basically the volumetric flow rate of supply air divided by the volume of the ventilated space, in an hospital, it becomes all the more crucial. And there's a basic formula which is Q equal to NB, where Q is the fresh air supply in meter cube per hour or cubic feet per minute, CFM, N is the air changes per hour, and V is the volume of rate. So a very fundamental formula which helps to get to basic thumb rule figures. So like ASHRAE states that the number of air changes, minimum number of air changes per hour in a standard residential room, small size residential room should be 0.35. But then this value varies from place to place, and in hospitals it becomes much higher. So in restaurant kitchens it becomes higher. In kitchens, normal kitchens also it becomes slightly higher. For it begins from the minimum value of 0.35 and then becomes 1 or 2 for some rooms. Or household kitchen it becomes around say 4 to 5 or 3 to 4 at least. Restaurant kitchens it will become something like 10 to 12. Classrooms it will become 6 to 8. So in that way, hospital sterilizing room it becomes 15 to 25. Hospital wards it becomes 6 to 8, and laboratories also it's between 6 to 15 depending on the type of laboratories. So, and here in this table you can see comparative air changes per hour in BC and ASHRAE. They will be mostly the same. They are very both very well researched, well documented guidelines, and they are mostly the same. A little bit here and there sometimes is there, but mostly the same. Here in this case they are exactly the same. So set number of, and these have to be followed. These become very crucial. These become a matter of life and death. Other spaces it may not become a life and death issue. In a classroom, in a lecture hall, in an auditorium even, people will adjust. Maybe they will feel a bit uncomfortable, discomfortable, but they will adjust. But in a hospital it becomes life and death. So it's very important, and it's connected with energy efficiency, obviously. So if you look at the ventilation standards, as per the ASHRAE, whose Indian version is ISHRAE, is the same obviously. If you look at it, we'll see that the ASHRAE standard 62.1 is actually it follows the basic guidelines for the amount of fresh air that should come in, the number of air changes that would happen, and there are 3 types of procedures: indoor air quality procedure, ventilation rate procedure, and natural ventilation procedure. Now, natural ventilation procedure is something that we have in our households, where it's nighttime we are switching on the split AC, but daytime we are mostly keeping the window door opens, and we are relying as far as possible, unless it's too hot, we are trying to rely on natural ventilation. So that is not being discussed here. Here is mainly about indoor air quality procedure and ventilation rate procedure. Ventilation rate procedure is very important because it defines exactly the amount of conditioned air that has to be brought in to the conditioned space, and also the amount of fresh air that needs to be brought in to the conditioned space at timely intervals, right? Because there is a mandatory amount of fresh air requirement also that should be brought in. Energy recovery ventilators help to do that. Then there are fans, exhausts, everything obviously in place. And standard 62.1 is aimed at basically having maximizing energy efficiency of the ventilation systems, as well as providing indoor air quality of a reasonable standard to the human occupants, so that they don't have adverse health effects. If we look at the ASHRAE 62.1 and what they say regarding the airflow rates, obviously the size and orientation of the building matters a lot. That is the basic determinant. That's why architectural design properly done is so important of the heating and cooling load. Then the other factors, obviously, as we are aware of, are occupants, number of occupants, type of equipments, appliances used in the building. Now, a minimum ventilation rate of 20 cubic feet per minute per person is required as per ASHRAE. And duct sizes, they recommend ASHRAE as its recommended duct speeds, velocity of the supply air ducts and the return air ducts, which are 600 and 900 feet in a range of 600 to 900 feet per minute for the supply, and for the return air duct is between 300 and 600 feet per minute. Aspect ratio between the duct is 1:1 or 1:1.5:1 for round and rectangular ducts. But CPW standards vary a little. Here, if you notice in the ratios, the CPWD standards will be similar. They also have ideal ratio is 1:1.5 for rectangular ducts, but it's a little different. So, and then duct insulation should always be there, because otherwise it will become a very energy inefficient system. So maximum, that's a common thing. Duct insulation is done everywhere. So, and then ASHRAE has other standards also. Like we spoke about 62.1, which is the most crucial one. 62.2 is about particle filtration mainly. And it talks about HEPA filters, and then it's more followed up in ASHRAE 170, which also talks about all the various types of filters and how through filters we can filter out the existing microbes. So HEPA filters, which is high emissivity particle arresting filters for ICUs, OTs, isolation rooms. Then we have some special types of filters like ultraviolet germicidal irradiation for HVAC ducts. That is also one type of filters used. Above a certain wavelength or frequency, below and above a certain wavelength and frequency, the germs are killed off automatically. But of all these, the best performing one is the HEPA one. In COVID time also, HEPA filters were very effective. They are more reliable. So then there humidity control also has to be done in a hospital rooms. Obviously, it's very important. So, as I said, more important, relevant for a hospital HVAC design is the IAQ procedure and the ventilation rate procedure, right? So now we come to the HVAC considerations, right? Now we come to the HVAC considerations. If we come to the HVAC considerations, we will see that, sorry, the sizing and zoning of HVAC systems. So from an energy efficiency point of view, it's very important not to oversize a system. Oversizing can contribute to poor air distribution and insufficient dehumidification. And zoning based HVAC systems is also very important. So oversized heating systems can cause short cycle, and systems that short cycle will deliver either in case of cooling, it will deliver cold air in short bursts, but will not function properly, and it will not dehumidify the air. So, and then there are, and also cause more energy consumption. And then HVAC systems also, as I said, energy efficiency and indoor air quality go hand in hand. So HVAC system may be contaminated because of mold in duct lining and insufficient cooling, overcooling. All these also contribute. Dehumidification, excess humidification, all these contribute in their own ways to making IAQ also improper. Some like over humidification may cause growth of mold in duct lining. Then excess dehumidification, less than required humidity will cause other issues, dryness. So HVAC duct distribution can even spread pollutants from one portion of the hospital to another, and it's very important to properly maintain that as well, and do duct sealing as well, have proper dampers, valves which control the flow of air. So undersized and oversized ducts can both lead to pressure imbalances, either reduced or excess airflow, and increased energy use. Obviously, it will become energy inefficient. So optimizing the duct sizing is very important. That's why CPWD, ASHRAE, ISHRAE, everyone has their proper duct sizing ratios. CPWD 2019 has its own manual of HVAC, and it details out all these things. Determining and calculating the required airflow rate, that's where the ventilation rate method comes in. So by the ventilation rate method and the indoor air quality rate method, both in conjunction with each other, we need to actually calculate a certain, the MEP engineers along with in consultation with the concerned architect has to calculate the proper airflow rate required as per, and so the entire duct system design will be based on that. Nowadays, we also have computational fluid dynamics, CFD software that can simulate the airflow and pressure distribution in duct systems. So that's an advantage, providing insights into the performance and energy efficiency of different design options. The use of variable VAV systems, variable air volume systems, can help optimize HVAC duct sizing by controlling the airflow rate to different zones in the building based on their occupancy and heating and cooling requirements. This can reduce energy consumption and improve occupant comfort. Conducting regular maintenance and testing of the HVAC system can help ensure that it is operating efficiently. So we need to actually check for leaks, clean filters have to be cleaned time to time, and airflow rates have to be adjusted as and when required. So that facility management team should constantly monitor, and there should be a checklist. So what are the main challenges regarding energy efficiency and IAQ in hospitals as on date? Over or under cooling, of course, to sum up, air leaks, poor airflow, dirty ducts, improper duct design, inadequate insulation. So, and lack of zoning-based system, because zoning-based system actually reduces energy consumption and ensures temperature consistency. And then hospital design, HVAC design is always more challenging. Obviously, burn patients, they will require higher ambient temperature. And then there are, obviously, the total amount of energy consumed is also much more in hospitals. And humidity management is also more critical. Like operation theaters, they need a certain set of temperatures. So it makes actually VAV system even more crucial for hospitals. Like operation theaters need to prevent bacterial growth and maintain the sterile atmosphere to prevent infection growth. ICUs have to ensure patient comfort and minimize infection risk. Patient wards and recovery rooms have to maintain comfort and energy efficiency. Sterile storage areas have to prevent degradation of sterile medical supplies. So they have different requirements, and as per that, they have to have the temperatures. Now, a lot of common features are there nowadays. Active design systems like radiant cooling and chilled beams, airflow and ventilation for comfort, thermal insulation, enhanced thermal insulation, and then there are the smart temperature monitoring automation, as well as the traditional methods of passive design strategies as well there, passive cooling strategies. So what are the basic thumb line rules for HVAC considerations? So we have to first obviously calculate the cooling and heating load, load calculation based on, and then perform zoning based on occupancy. Based on occupancy pattern, thermal load, and individual comfort requirements, because that impacts the required airflow rate and ventilation requirements for a space. Then we need to determine the required airflow rate for each zone. So, and it is based on the total heating and cooling load and the desired IAQ. IAQ will be ensured by having proper number of air changes and fresh air intake. Providing adequate supply of fresh air by incorporating mechanical ventilation systems that deliver outdoor air to occupied spaces, and consider using heat recovery ventilation systems or energy recovery ventilation systems, HRVs or ERVs, to minimize energy losses. The type of HVAC system being used will also impact the size and layout of the ducts. For example, a centralized system will require larger ducts than a decentralized system with smaller localized units. And the duct layout must be designed to minimize frictional losses and pressure drops. So appropriate duct size, shape, and layout are very important. And there are appropriate duct size tables available in ASHRAE, as well as a lot of softwares available, as well as CPWD guidelines give detailed guidelines. So, like for example, if you look at the CPWD considerations 2019, the size of HVAC ducts in an office building should be determined based on the airflow rate, same as what ASHRAE says, and which is again determined from the cooling and heating load of the building, the size, which again in turn depends on the size and orientation of the building, the number of occupants, and the type of equipment and appliances used in the building. The air velocity in the main duct should be maintained at 400 meters per minute, and branch ducts should be 250 meter per minute. And the maximum velocity at supply air grill diffuser is 150 meter per minute. I mean, I just out of curiosity, once when teaching my students, I worked it out. It comes to be at more or less like 10 meters per second or something. So 600 meter, 60 seconds. So it will be like 100-meter dash, champion sprinter 100-meter dash, whatever. So there are standard air velocities which have to be maintained from with the proper duct sizes, and the total airflow rate has to be calculated appropriately. So the air velocity in the ducts should be between 10 to 12 meters per second, as I said, for supply ducts, and 8 to 10 meters per second for return ducts. Right. So duct size width to height ratio of 1.5:1 or 2:1. That is what CPWD recommends, because square ducts is not always possible. So mostly rectangular ducts from a supply design point of view and a fitting point of view, with the proper clear height ceiling, rectangulars are better. So architects and MEP consultants, they usually prefer rectangular. So 1:5:1 or 2:1. And then duct insulation, the duct should be insulated, otherwise it will lead to energy inefficiency. So actually 10 meters per second will be that 100 meters will be in 10 seconds. So it's like Usain Bolt running. So the size of the duct is governed by the thumb rule by two factors. Obviously, it is basically cubic feet per minute, the feet and the cut cross out, and what remains is the meter square, which gives us a theoretical cross section of the duct. That's a very thumb rule method of the cross sectional area of the duct, where we can, from the total amount of air in cubic feet per minute, by dividing by the velocity of air in feet per minute, or whatever the appropriate units, it can be meter per second, anything, instead of cubic feet per minute, it will be the SI units also. So, but what you are left with is the meter square, which gives a very rough thumb rule cross-sectional area of the duct. So, for example, for a waiting lobby space of 100-meter occupancy, amount of air per person is 20 cubic feet, which, so as you may be remembering earlier in the presentation, I told you amount of air required per person as per ASHRAE standards is 20 cubic feet. So, 100 people, it will be 100 into 20 cubic feet, which will be 2000 cubic feet. So air velocity feet per minute can be taken as 400 meter per minute, and it results in duct size, which is 1.524 square feet, which is 1.23 into 1.23 duct. So this is a very thumb rule calculation. There are softwares available. There are mathematical methods referring to ASHRAE tables and CPWD guidelines, which will come to the exact point. But to quickly have an idea at the design stage to how much clear height to keep and all those things, these will come in handy when the architect is finally sitting with the MEP consultant. So the air should be conveyed as directly as possible to economize on power, material, and shape. Air velocities in ducts, as mentioned, should be within permissible limits to minimize losses. Rectangular ducts should be made nearly as square as possible. Most effective is square, like same like buildings, like in hot dry areas and cold climates, we say that buildings should be as compact as possible. Obviously, square and circular shapes are most compact. They will be most energy efficient. They will lose least amount of heat. It will be easier to, because they have the least exposed surface area for the maximum volume inside. So same for ducts also. It can carry the compact ducts like square and circular can carry the maximum amount of air without having the least amount of exposed surface area. But as for easier design and other considerations, the rectangular ducts should be, usually we go for rectangular ducts with a ratio of about 1.5:1, and but it should be as squarish as possible. Then dampers, which regulate the valve within ductwork, especially at duct junctions and branch outlets, should be provided, because they are valves basically which control the flow of air. When not needed, they will just stop. So if we look through all these, the things discussed in the last 2-3 slides, what are the steps for multi-zone sizing using the variable air volume system? Find the sensible heat gain through conduction, convection, radiation, and internal heat gains, right? Find the capacity of the AHU in cubic feet per minute by calculating the tonnage of refrigeration required and using the thumb rule. A very basic thumb rule again is 1 ton of refrigeration is actually 400 cubic feet per minute air volume, right? Pick out the dimensions of the AHU by identifying the appropriate AHU from the product catalog and sizing. All these major air conditioning companies have product catalogs, which as per the amount of air, they will tell you the AHU room accordingly. Right, zone out the spaces that need to be conditioned with the VAV system based on occupancy and the orientation. Model software simulation models are also available for this. And the orientation or number of exposed surfaces for individual zone control for the multi-zone VAV system. Size the main ducts and branch ducts of each zone appropriately. Size the VAV terminal box by identifying the dimensions from the product catalogs based on the ventilation rates of each zone. VAV terminal box is the one which controls the airflow to different zones, because it will act as a regulating mechanism to the different zone airflows. And then finally calculate the amount of outdoor fresh air required for the occupancy based on the ASHRAE standards. So all these steps are very simple basic steps. There is much more detail to it, but for us architects, at least we should be aware of these basic steps when we are dealing with energy efficiency and all these issues in hospital design, because energy efficiency has now progressed much beyond the basic things. We can't keep talking about the basic things. We have to know a bit more in detail, and we have to now engage with the MEP consultants in a more knowledgeable way as architects, so that energy efficiency is actually implemented, because MEP consultants won't be usually bothered about energy efficiency. They will just see the job done and just walk out, project closed. So we have to be more proactive. So if we look at a simple calculation, the occupancy is 40 people, just assume. Internal heat gain due to 1% is this much British thermal units per hour. So total heat gain due to all the various factors. There are formulas for all these: conduction, radiation. These are the four main types of heat gains considered in very simple base case calculations: conduction, radiation, convection, and internal heat gains. And then we get to 6 tons. As I said, 1 ton of refrigeration approximately requires 400 cubic feet per minute of supply air, conditioned air. So 6 tons of refrigerant is so much, 6 into 400, 2400 cubic feet per minute. Now, considering the model and referring to catalogs and ASHRAE, AHU dimensions will be 7.5 into 4.5 into 2.6 feet. And adding circulation space, we get a total AHU room size, which is close to 194 square feet. Considering 20 cubic feet per minute of outdoor air per person, 800 cubic feet of outdoor air is required. So therefore, from that, you easily get the baseline thumb rule calculation of how much outdoor air is required. These are very simple calculations, and since we here at SBA Vijayawada have our masters in sustainable architecture, a lot of other institutes, I think NIT Patna also has. So we should, when we are teaching subjects like healthy building at master's level, or enhanced indoor environmental quality subjects, we try to incorporate these practical aspects also into the courses, so that actually students at least have an overview of what energy efficiency means in the truest sense in hospital scenario and all other such situations. So, and duct sizing is also obviously can be found out with the amount when we know the volume of air and the ventilation rates, and we get in square feet the duct sizes, and we also get the diameters. So, of course, energy recovery ventilation, ERVs or HRVs are very important. They help in reusing some part of the return air as well. The cooler part of the returning air is, instead of all the air being wasted or being thrown into exhaust, they take back some of the air which is already cooled. So the amount of energy they have to put into cooling that air is lesser than the amount of energy they would have to put for normal temperature air. So a little bit of energy is obviously saved, and also it can serve as a mechanism for fresh air intake in a controlled way. So if you look at a checklist, we should the MEP consultants and even in the project facility management team should examine the building air intakes and ducts. They should keep reviewing the air distribution system, whether the ducts filters need cleaning, are molds growing in the diffusers, the amount of fresh air being needed to be supplied to the space needs to be worked out, and the equipment locations, everything should be worked out. So IAQ maintenance system obviously plays a major role in protecting health through air quality maintenance, controlling the parameters of temperature, humidity, and ensuring building systems are operated efficiently, increasing energy efficiency. Now, even this indoor air environmental quality, it depends a lot on how we have the ventilation, whether it's spot, some areas require spot ventilation, even in an hospital, like bathrooms, kitchens. Whereas where there are more amount of contaminants and it has to be exhausted out. And then the other areas will be having dilution ventilation. So obviously HEPA filters, as already mentioned, it plays a very important role in the indoor air quality, indoor environmental quality. And then also there are other guidelines like the Air Conditioner Contractors Association, SMACNA guidelines, which talk about duct sealing on the return side, side drawing of the air, and all other aspects. So if you, this is taken from the IGBC Green Healthcare Facilities, our COVID times healthcare A. So they had a COVID healthcare facility where they zoned it properly, and then there are different zones, level 1 area, level 3 area. So it's an example of how efficient zoning is so much important, which was, and that's why it was featured as a study for the IGBC healthcare facilities. And then duct pressurization is also very, very important. So obviously in here, our case will be more with mechanical ventilation. And air conditioning. So air conditioning with AHUs. So the thing is that duct pressurization, the pressure in the duct should be maintained. The pressure gradient should be maintained, and the AHUs should induct fresh air. That obviously, because fresh air intake requirement is a mandatory requirement, and it will also create the necessary pressure gradients when the AHUs induct the fresh air. So again, zoning, zoning helps both functionally as well as further from the surfaces point of view. If it's neatly zoned, if it's compactly zoned, if it's properly zoned, it helps a lot. So IGBC green healthcare facilities is also existing, as some may be aware, and obviously that also covers a lot of energy efficiency features. Now, like if you see the energy efficiency features, you'll see all these are the energy efficiency requirements, like which also includes renewable energy generation, proper energy metering and management, energy efficiency, either the whole building approach or more easily the prescriptive approach based on ECBCA. So it's already there. It's only that, and if you actually look at it, a lot of, if you see orange is energy efficiency. So 23% of the IGBC healthcare facility rating systems also deal with energy efficiency. And so obviously this is the overall process. Project registration, project team submits the preliminary documentation for review. Then there is review by the IGBC third party assessor. The final documentation is then submitted. There is a visit to the healthcare facility, and then the rating. But and it is obviously supplemented by energy audits, environmental parameter measurements, and proper building operation and maintenance procedures. Now, but other than IGBC, also there are a lot of other more advanced rating systems which take more care of the energy efficiency part and the indoor environmental quality part, like lead operation plus maintenance. And then the SIPSE, which is a Chartered Institution of Building Services Engineers, Australia, and BREEAM, Building Research Establishment Environmental Assessment Method, UK. BREEAM is very effective and it pays very specific emphasis on services. And then there is LEED well, which has come out from LEED only. And well, the advantage of well is that it covers additional topics like microbe and mold control, pesticide management, water quality control, all these things as well. So, and building wellness, it has been basically derived from the LEED, operation and maintenance, and ASHRAE. So, like if you look at mechanical spaces, again, they talk about the minimum air changes per hour for different categories, different rooms, and we'll look at the air conditioned cases only, and not the naturally ventilated cases. And then the daylighting, so the percentage of areas with daylighting, and so they offer points as per that. Now coming to the other services, if you look at the other services, basically other services are also important, but HVAC is most crucial from a point of view of enhanced energy efficiency. So if you look at the other services, water management and plumbing, NBC recommends dual stage filtration for critical areas. Obviously it does, and mandates low flow fixtures. ASHRAE 188 is there for water safety, safe water with Legionella bacteria prevention and water safe water temperatures, because there is a certain temperature of water in which microbe growth is more. So that that temperature of the water should not reach that temperature. And ESHRAE also has some guidelines. So then there are filtration and water purification guidelines, reverse osmosis and UV filtration are required for some specialized areas like dialysis centers and surgical and ICU units for removing the toxins and ensuring ultra pure medical water. And obviously the sustainable water practices which are very much there in ECBC, as well as now integrated into bylaws of also some states like Andhra Pradesh has it integrated into the bylaws as well, like rainwater harvesting, which collects rainwater for non-potable use, and grey-water recycling. And obviously nothing works nowadays without smart plumbing and leak detection. So IoT-based sensors which detect leak, track water usage, and automatic shut-off valves, smart meters for real-time monitoring of hospital water consumption. These are very much standardized things now in India as we are modernizing, and these should be also implemented. If you come to lighting and daylighting, hospitals it's a place where patients are there, so they have their issues. They're going through trauma, they're going through illness, they're going through psychological issues. So soothing lighting helps. Like there is something known as circadian lighting systems, which follows the heart patterns of the. So it adjusts color. Smart lighting systems basically which adjust color, temperature, and intensity to mimic natural daylight cycles. Then there are slightly warmer tones in patient rooms for relaxation, slightly cooler tones in ICUs and operation theaters for alertness. And then there are different lux levels, like patient rooms, it should be just above or equal, just about equal to 300 lux. Nurse station, you require up equal to or more than 500 lux. Surgical sites, obviously, suits, obviously retail concentration, so you require anything between 500 to 1000 lux. Corridors and waiting areas, you require 100 to 200 lux standard values. So then some strategies which hospitals use are use of the skylights and large windows, use of light shells and reflective surfaces, double glazed windows, and the standard energy efficient lighting solutions like LED lighting, motion sensors, and dimming controls, so that if you don't move for some time, it doesn't detect movement, then it will auto switch off. Then solar powered outdoor lighting to reduce renewable energy use to reduce energy demands. These are standardized things nowadays in many buildings, be it guest houses, hotels, hotel washrooms, everything. Then there is obviously one more thing that we need to keep in mind is efficient, safe water management. So solid waste management system has to be automated, and there has to be automatic waste collection systems to reduce human interventions and exposure in handling hospital waste. Especially in case of hospital waste, it becomes very crucial because of some infectious waste and contaminated waste like biomedical waste and all those. So here automatic waste collection systems which handle 95% of the total waste, including biomedical waste, helps a lot obviously for the safety, health of the workers as well. Acoustics, again, we have NBC 2016 also. NBC covers everything. All the basic things is covered regarding all services, obviously. So not exceeding sound levels, since they are more sensitive to noise. It should not exceed 35 decibel in patient rooms and 45 decibel in ICUs. And then there are some things that ASHRAE 170 also specifies regarding sound transmission ratings for the wall materials and partitions to minimize noise transmission. And then there are some soundproofing strategies like sound transmission class height STC walls between critical hospital areas. Negative and positive pressure zoning also helps in preventing noise leakage. As mentioned before, the air, the start of the presentation, acoustic treatments, obviously it always helps, ceiling acoustic treatment, wall acoustic treatment, HVAC noise reduction, wherein we use low noise air handling units and vibration dampers are used in mechanical rooms. And soft closed doors, silent nurse call systems, reduced paging systems, separate emergency and patient care zones to limit disruption. Zoning, again, that's why in the initial start of the presentation, I said zoning is very important. Zoning helps to make a lot of things easier from the surface point of view at a later stage. Then finally, obviously, smart building and automation. So many buildings we have where smart buildings are being used in a very advanced way. Like famous example is Gift City buildings. The building automation at its best, building management system at its best. So all those can be used to, to actually control, monitor the use of energy, monitor the use of water, ensure there are no leakages, ensure there is no wastage, and also have automated AI-based, IoT-based system, AI-based ventilation system. If AI can be done for lighting, when there are no movement is detected, lights dim, or when lesser movement is lights dim, then the same thing can be done for ventilation systems also. So we can, there can be adjusting of airflow as per occupancy, same as lighting systems are done. Similar to that, real-time air quality monitoring with HEPA filters, they are already been done. UVGI systems as already told. Smart lighting systems as also discussed right now in 2 to 3 slides before. AI-enabled infection control, IoT-based energy management, smart meters for real-time energy tracking, demand-based power regulations for non-critical hospital areas. And these show how smart lighting can automatically adjust lighting levels, right? So the way ahead, obviously, there's a lot to be done. Some high-end hospitals are doing, big international hospital chains, they're trying to do some aspects, but most of the hospitals and nursing homes, they are lagging in these things. So most have to catch up. So we have to create a standardized basis for identification of ZEB strategies for hospitals. We have to have measurable and verifiable indices as said at the beginning. We have to reassess design and operation of building services and all its associated components to optimize and reduce energy consumption. Have easily understandable guidelines. If the guidelines are too complicated, industry and policymakers will be lost, and then that can be implemented. We have to have short-term and long-term goals. We have to provide an environment that assists in heat balance of the body. We have to periodically dilute indoor air with fresh air to eliminate contaminants and odors, because as I said many times, energy efficiency and IAQ and IEQ are very interlinked in a hospital situation. We have to use building energy management systems to the maximum, and we have to integrate CFD with dynamic building simulation models. So computational fluid dynamics modeling has to be integrated with the simulation, energy simulation, whole building simulation method models as well. So these are some of the references I consulted, and thank you for patiently listening to me. Yeah, I'm done. Hello. Hello. Am I audible?
Yes.
Yes, sir, you are audible. Thank you very much.
Yes, sir. Yeah.
So any queries, anything? I hope it was informative and hello. Hello.
Hello. Hello.
Any queries from anyone? Oh, acha, some messages are there. Okay, thank you. Yeah, it is nice to know that it contributed something. Thank you. So anyone who wants to further correspond, they can also contact me on my email I'll give here. They can correspond if they have further queries. In case questions are not coming now, I'll type my email ID.
Hello, everyone. I'm
So I've typed my email ID. Anybody who is looking for further raise in energy efficiency areas can correspond to this.
On behalf of the organizing team, give me a minute, sir.
I'll mute.
Hello. Hello. Yeah. Now I think my voice is good. On behalf of the organizing team and all the participants, we extend our heartfelt thanks to Dr. Janmejoy Gupta for his insightful and engaging session today. Your talk addresses a critically important aspect of sustainable design and public health infrastructure. The depth of your knowledge and the particle perspective you shared and added immense value to the faculty development program. We are truly grateful for the time and effort you took to be with us and to enlighten our participants on such a relevant and impactful topic. Thank you once again, Dr. Gupta, for your valuable presence and for making this session a great success.
I think there's one question as I was just looking. If an existing building has a split AC, that is unitary AC system installed, and they wish to improve, that is the main problem. Fresh air intake is a problem in unitary AC system, right? There is no way in which you can actually let in fresh air. Only way you can let in fresh air is to open the window from some time to time, which will lead to energy inefficiency, right? So in unitary AC systems, split AC systems, it is difficult. That's why centralized AC systems, all these things, basically what I said today was for proper hospitals, big scale hospitals with centralized AC systems. All these systems work better if they're centralized AC systems. In a unitary AC system like split AC, it is some supplementary systems can be used, but they become very costly and they are not worth it. Fresh air injectors, how would you, the only way in which some fan-based system, right, which will let in fresh air in a proper way, which will become something like an energy recovery ventilator system only, right? So, a fan-based, exhaust-based system which can inject in some fresh air, yes. That can be installed, but it won't be cost effective. It won't be cost effective, right? It won't be cost effective. For a unitary system, for a nursing home, small nursing home, which has say 5 rooms, 10 rooms, and each of them have a split AC, it won't be very cost effective if you have fresh air injections in that way. I hope that answered your question. Okay, is that all?
Sir, one doubt.
Yes.
Like there are many references for standards, like you have discussed about ASHARE and ESPC,
ASHRAE, yes.
yeah, and NBC,
ECBC,
and
yes.
this now NBC 2025 also coming. So
Yes.
why is like there's no compilation of these standards in one single document, or
no, sir. Actually, ECBC has included everything from NBC only. NBC, as we all know, came first, right?
Yes.
ECBC is basically a lot of things have been taken from the NBC and then added upon from the sustainable point of view and the energy conservation point of view. NBC is not only for energy conservation. NBC has only some sections which deals with sustainability. NBC is about everything related to architecture and buildings, right? So ECBC came for more specialized energy conservation part, and it has taken the relevant parts of from NBC. Similarly, ashtray came, ashtray was started from America basically. The first issues of ashtray first versions came long back, around 1970s, late 1970s, that time. And then it kept on improving and upgrading. And again, ECBC has referred to ashtray as well as NBC when it obviously ECBC was compiled by a group of big experts all over India at that time when it first came into being compiled early 2000s. 2007 first draft version came in. 2017 it was accepted. So that time it has taken into consideration all, and you will not find any conflict, as I showed also today, between the NBC and the ashtray, you will not find any conflict. So they have looked into each other's documents while compiling, and there is no conflict. But they each serve a particular purpose. So that's why compiled version for Indian purposes, it will be very convenient if we stick to ECBC. Actually, Energy Conservation Building Code has everything, and for additional information, the concerned services regarding the concerned services, if we refer to CPWD, that's my personal understanding. That way, it will be easier and convenient.
Thank you, sir.
Okay, so I think it is done. Any further query, you can also mail me, right? So thank you, organizers. Thank you, NIT Patna. I think it is a bit early, but it's fine. I mean, the presentation, I had all that I wanted to say, I could convey it within this time only. But in case there are more queries,
thank you so much all the participants for your active participation. So with this, we end the meeting now, and we will meet tomorrow at morning. Okay. Thank you, everyone.
Okay. Thank you. Thank you.